In this video, we will look at case 1 again, continuing with the case where we have a normal population and a known sigma, and we will focus on calculating the probability of a type 2 error as well as the sample size that we require. Now, we'll look at example 19 again, the edited version of example 19 in your textbook, or question 19, and there we had that we wanted to test the hypotheses that the mean is equal to 94 against the alternative that the mean is greater than 94. Now, we've already defined our alpha in this question specifically as 0.01, so that is just the risk associated with a type 1 error, which is of course the probability of rejecting the null when we shouldn't have, because the null is true. Now, if we indicate that on our graph, and always draw graphs so that you can visualize your problems, then this is what our rejection region would have looked like. And now next we might ask, what is the risk associated with a type 2 error? So we know that beta is the probability of a type 2 error, and a type 2 error is of course just the probability of not rejecting the null when the alternative or some value under the alternative is true. Now, type 2 error, we therefore need to calculate for specific values under the alternative, and that we will denote with a prime. So let's say mu prime is our value and that we want to calculate a type 2 error for under the alternative. Then we will call it mu prime, and we'll use the example here of 95. So the notation we will then also use is beta of 95, so that will tell us this is the probability of committing a type 2 error if we assume that the population mean is now 95. So that is a value assumed under the alternative. So we'll look at that in this specific question. So we have our null and alternative up there on the right hand side, and I've also put the definition of beta. So it's always a good idea whenever you do questions to do with type 1 and type 2 errors, write down the probability statement and use that as your starting point. That way the problem becomes much easier to solve. So we're going to look at beta for mu prime equal to 95. Now, first thing is we want to just visualize the problem, and we do that by looking at this graph, and I've indicated there using alpha. So we've defined that we want alpha to be equal to 0.01, which means that the area to the right of my critical value is going to be 0.01. So that is the rejection region. And then the area in which we don't reject lies to the left of the critical value. And remember, this is a right-sided test. We know it's a right-sided test because we look at the alternative, which says greater than. Now, if we were doing a left-sided test, we would have a left-sided rejection region. A two-sided test would be a two-sided rejection region. So we'll just focus on this one example here. Now, we said already that beta is going to depend on the true value of mu, in other words, the value that we're denoting by mu prime, and we need to keep that in mind when we do our calculations. So let's say this value we've given you as 95. We'll always give you this if we want you to calculate a probability of a type 2 error. We would have to tell you which value to calculate it for. You can go and do this for multiple values, and we'll get to that in your practical, because it's quite easy to do these kinds of calculations on software like R. Even in Excel, it's quite straightforward. But yeah, we'll just focus on one specific value for the moment. Now, let's say we want to calculate beta of 95. Then that is the probability that the null is not rejected, given that the mean is actually 95. So we'll start by writing, what does it mean, null not rejected? We know the null will not be rejected in this region that I've indicated with the green arrow, which means if Z, our test statistic, is less or equal to 2.326. So that was my cutoff point. If you'd used 2.32 or 2.33, that would have been fine. I got mine, you would have seen in the previous video, accurate to 3 decimal places using the t-tables. And it's nice to be able to get it a little bit more accurately instead of having to guess from the normal tables. You can, of course, also use R and get your answer even more accurate. Now, we're still keeping in mind that the mean is now 95. So we're assuming here that this is the actual mean of the population. Now, we can expand this a little bit and think, but this Z, this test statistic that we have over here, is actually just x bar minus mu naught over sigma over root n. So this is x bar minus its mean under the null hypothesis divided by its standard deviation. So the standard deviation of x bar, which is also known as the standard error of x bar. So we would reject the null, or we would calculate beta by saying this is the probability that this whole test statistic over here is less than or equal to 2.326. So that is the probability of rejecting the null. But we need to still keep in mind that we are dealing with a case now where mu prime is 95. So that is our new population mean, or the actual population mean under the alternative that we're considering. So what I've done here is I've just substituted in the place of this Z. I've just gone and substituted this definition of Z, and then we solve for x bar. So we want to get x bar alone on the one side. So you can see that we're still reminding ourselves all the way that this is now the population mean. So here we're standardizing in our test statistic using the mean under the null, but we eventually want to standardize using the mean under the alternative. So we first need to get Z on its not Z, x bar on its own, so that we can then standardize again. So that's what we've done here. We have literally just moved everything over to the other side. So we first multiplied both sides of this inequality with sigma over root n. So that's what happened in this first step. And then we just added mu naught to both sides. And that means that we end up with x bar on the one side and then this value on the other side. So, and we're still reminding ourselves that mu prime is now 95. So next, we have this specific value under the alternative, and we know that if mu prime is the actual population mean, then x bar is actually centered around mu prime. So in other words, in this case, x bar is centered around 95 and not 94, which we have under the null, which means that we can now go and calculate this probability. So now all we do is we go and standardize using the actual distribution, this new distribution of x bar. So we are assuming that the variance or the standard deviation of x bar remains the same. You can see that when we standardize, we're still standardizing with that. But all we've done now is we've taken this equation that we have over here and we said, well, to get x bar standardized and back to Z so that we can use the standard normal tables, we need to subtract its mean. Its mean is now 95. So that's why I'm subtracting 95 on both sides. And I'm dividing by the standard error. So if you look at those two steps, you'll see that's all that's happened. Which means that I now have a Z again. So this bit that I have on the left-hand side is actually just Z under the alternative. And if we simplify this term, you can see we end up with that term over there. And if we do that calculation, remember we'll plug in the sigma, which is 1.2. We'll plug in the n, which is 16. And we end up with a Z value here on the right-hand side of minus 1.01. And if you go to your normal tables, you will find that cumulative probability is 0.1562. So you can go and maybe try this and see what happens if we do this calculation for another value of mu. So maybe use mu prime equal to 96, or maybe have it equal to something a little bit closer, 95.5, something like that, and go repeat this calculation and see how that changes your answer. And you'll see all the only thing that you need to replace is actually that value there, with the new value of the population mean under the alternative that you're interested in. Now, why does all of this make sense? So this is just, again, a way of visualizing it. So if we look at our distribution of x bar under the null hypothesis is centered around 94 in this specific question. So alpha, we know, is the area indicated in red. That's, if we're doing an upper tail test, that's our rejection region. And now we need to think, but what happens if my mean has actually increased? So if we draw a sketch of that, that just means if the mean has increased, remember we're keeping the variance and the standard deviation the same, but if the mean has increased, it just means that our entire graph has shifted. So it's just shifted to the right, and it's now centered around this new mean. So when we're calculating beta is just, so we've just indicated it here, beta is the probability of not rejecting the null. Now, if we look at this first sketch, the probability of not rejecting the null in this first one, if the distribution is centered around 94, will be the area to the left of this critical value. But if I have shifted my distribution, then the probability of not rejecting the null will change, because we still have the same cutoff point here, but you can see everything is shifted, and you can see that now the probability we're calculating is actually the area to the left of that critical point, but it's smaller than we would have had in the first case because it's shifted. So then we can think about sample size. We'll get to sample size just now. So if we want to minimize this area under the curve to the left of that rejection point or the critical value, then the only way of doing that is to actually affect the standard deviation of this curve. So let's say we're fixed on the 94, we're fixed on the 95. Those can't be changed. Those are the values we're interested in specifically, but we want to minimize beta, and we'll get to that at the end of this video. Only way to do that is to change these curves. So if we can reduce the variance under this curve or of these values, of these x bar values, then that area under the curve will become less. So if it becomes a taller graph, then you can kind of visualize it going a little bit taller. This is a horrible graph, but yeah, you'll see the area will become smaller under the curve. And that happens if we can reduce the standard deviation of x bar, which is just sigma over root n. So we'll get to that point just now. We'll first just do a derivation, slightly more formal derivation for how to calculate beta, and then we'll get to the point where we can calculate the sample size. And you can see that if we increase this n in the standard error, then the standard, so let's say n is increased, then the standard error, all of this term, is going to decrease, which means the curve is less spread out, it becomes taller, and that area to the left of the critical value will become smaller. So that's the logic that we're working towards. Now, as I said, let's quickly look at the determination of beta first, and then we will look at the sample size. So let's see if we have a upper tail test. So we'll specifically focus on this upper tail test. We've done a specific example now. Now we'll do the more general one. We have our rejection region to the right of our critical value. And you should be able to go do this derivation for a left-sided test as well. We'll talk about that just now. But we've already seen that this statement that we will reject we have a rejection region when z is greater than z alpha is the same as saying we'll reject the null if x bar is larger than mu naught plus z alpha times the standard error of x bar. Now, we won't reject the null if we swap this around if x bar is less than mu naught plus z times the standard error. So, and we're using mu prime here for a specific value of mu that we're interested in that exceeds the null value, and exceeds in this case means larger. Exceeds in the left-sided case is actually if it's a smaller value. So it's something more extreme than what we think the null is, and extreme is in terms of the alternative, so how we've defined the alternative. Now we've said then that beta of that mu prime is just the probability of not rejecting the null when the mean is actually equal to mu prime. And then all we did was we got x bar alone on the left hand side, and we saw on the previous slide how we did that. So you can actually go fill in, there's a few steps missing here. You can go fill them in yourself so that you understand the problem better. And then we just need to go standardize x bar using this new distribution. And that tells us then that the probability of making a type 2 error given the specific value under the alternative is going to be calculated as a cumulative probability from the normal distribution, and it's pretty much just plugging in values into the statement. Now, what you should notice is the larger this value of mu prime is, the more negative this term here is going to become. Because remember, if we just look at the sketch again, we have two values here. This is mu, and at this point, this one is centered, or sorry, let's call it mu naught. This is mu prime. So the larger mu prime becomes, if we take the difference between these two values, this value will become larger and larger, the difference, in a negative sense, because you're taking a larger value away from a fixed value, which is smaller than mu prime. And then that means that this term in here, this entire term, is going to become more and more negative. So the more and more negative it becomes, remember, if you think about a normal curve, the further to the left you are on your normal curve, the smaller the probability to the left will become. So it all makes perfect sense. So as we also move the value of mu prime that we're interested in, there will be less chance of making a type 2 error. So go think about it, visualize the problem again, and make sure you're comfortable with this concept. Now, alternative hypotheses that we considered, there's 3 cases, and you should be able to derive the one that I just showed you, and using the same logic, you should also be able to derive this formula here. This one, I'm not going to expect you to derive it, but you will be expected to use it. So all of these formulas, you need to be able to use them, but you don't necessarily need to derive all of them. Just make sure you can do the first 2. Then one extra little bit of information, if we say 1 minus beta, that is called the power of the test. So that is a very important concept in statistics as well. And if you think about it, beta is the probability of not rejecting the null when the alternative is true. So 1 minus beta tells us how powerful the test is. So what are the chances of us rejecting the null correctly? So yeah, if given a specific alternative. So don't stress too much about the power of the test. We'll get back to that again. But it is an important concept. So for now, all you need to worry about is 1 minus beta is the power of the test. So if I ask you to calculate the power of the test, you know how to do that. First, just need to find beta, and then you can say 1 minus that. Now, last little bit, sample size determination. And this builds on the previous concept. So we have alpha, we have beta, we know what they mean, and we can have a problem where we say we're going to specify, and this happens in practice, we'll specify the risks that we are willing to take. So we'll specify the probability of type 1 and 2 errors that we are comfortable with for a given value of mu prime, which will mean that there is a practical difference that we are interested in. So, for example, let's say we're dealing again with an upper tail test. We have a null and alternative. Let's say the mean must be greater than 1 in some situation, and we can still deal with it if the mean is between 1 and 1.5, but we want the difference. If we get to the point where the mean is actually 1.5, we want to be able to pick that up. And let's say the risk that we're willing to accept at that point will both be, let's say both of them are equal to 0.1. So you might get that someone says, well, this is a point where it becomes critical to me to pick up that there's a difference, and this is the risk I'm willing to accept for making a mistake and maybe not picking up the difference correctly. So we can make that even smaller. So if we do that, like I showed you in one of the previous slides, the only way to have these values fixed and pick up a difference at a specific point is to go and pick our sample size correctly. So if we look at the graph again, these are our two graphs. So the first one is the distribution under the null, and the second one is the distribution under the alternative given a specific value. And there's our cutoff point. So we already know that the area to the right of the cutoff point given the null distribution is our value of alpha, and the area to the left under the alternative distribution, that is our value of beta for a specific value of the mean that we're interested in. Now, just taking a step back to the previous slide that we looked at, we saw that beta is calculated as this, a CDF of a standard normal distribution, and you just have to do this calculation, and that tells you what that probability is. So we can go and rephrase this. Let's say that minus beta is equal to this term that we have here in this first equation. Then we can say, well, we want to specify the value of beta and then work our way back to figure out what n is. So we'll do that on the next slide, and it's very straightforward. And again, notice this is just for the upper tail test, so you should be able to do the same derivation for a lower tail test. But basically all I've done is I've said, well, I've just given this z value, z beta is the value on the previous slide. Let's just go back to it. It's this value here that we just derived in the previous question. And so we set those two values equal. And then we say, well, let's just go and solve for n. So we know what z beta is. We can find that from our tables. We can find z alpha from our tables as well, our standard normal tables. So if I go and I just work to get n on its own, I finally end up with that formula. And I want you to go and check that if you do this for a lower tail test, that you can also work your way to the same formula. You do not need to be able to derive this one. You do need to be able to apply it though. So both of these formulas you need to be able to apply, but you only need to be able to derive it for upper and lower tail tests. And that is pretty much it. So I think go and practice this. Go do some examples, specifically 9.6 and 9.7, and then also go work through the rest of exercise 19.